We're going to move into chapter number 13, start talking about work and energy. And when we get done today, you're going to be able to identify when work is being done and how to calculate work. You will be able to describe a relationship that exists between work and energy. You'll be able to calculate potential energy and kinetic energy. And then finally, what we'll do is we'll be able to compare and contrast those different forms of energy. Anytime you apply a force to an object and you get it to move, you are doing work. You know, studying for a test, that's not work. Holding something up is not work. But if you apply a force and you get that object to move, that's when work is done. But you have to get the object to move. So your definition of work is when a force is applied to an object to get it to move. Now, one thing I'm going to tell you is, as I said earlier, without motion, there is no work being done. Now, something else that I want to tell you about work is, if you have a force that's going to be acting, let me go ahead and get a color in here that we'll be able to see. If we have a force that's going to be acting that way, and we have, say, a distance that's going to be moving up and down, no work is being done, or vice versa. Notice how those two are perpendicular to one another. In order for work to be done, you have to have force and distance acting in the same direction, okay, or the same plane, meaning both of them have to be horizontal, or both of them have to be vertical. But if you have one horizontal and one vertical, no work will ever be done. You have to have your force and direction, or force and distance, going in that same direction. Well, work is going to be equal to force times distance. W equals FD. Now I'm going to go ahead and put the circle equation up here real quick. And if we go ahead and look at our circle equation, you're going to end up having work up here, force down here, and distance there. So work is going to be the one that ends up being on top. Now I'm going to be putting them up here in just a little bit, but you've learned that force is measured in newtons. You know that the SI base unit for distance is going to end up being the meter. And then finally, work, okay, and it's going to come up here, but it's going to be measured in joules, okay? And basically what a joule is it is a Newton meter. What is a joule's worth of work? Well, roughly they say what a joule is if you think of an apple in your hand, taking that apple from kind of your hip or your waist and bringing it up to your mouth and taking a bite. That's about a joule's worth of work. Okay, so force, as I said, measured in newtons. Distance, measured in meters. And then finally, there is that joule. Okay, and as I said, the joule is just going to be basically 1 Newton meter. The joule, it is a unit of work that is 1 Newton of force over a distance of 1 meter. And basically it's named in honor of James Prescott Joule. And the thing is, he was the pioneer in energy research. Anytime energy was being studied, James Prescott Joule was the individual that looked and studied it, so they went ahead and named it in honor of him. It says here we have 24,000 joules of work. We'll move an object 2 meters. How much force is applied to that object? Well, if you think back to our circle equation, force is going to be equal to the work done divided by the distance. If we go ahead and plug those numbers in, 24,000 joules worth of work divided by 2 meters, you're going to end up with an answer of 12,000 newtons worth of force was applied to that object. If you look at pages 406 and 407, okay, you're going to see there that you have a roller coaster. And I want you to think about roller coasters. I guess first of all, how many of you like roller coasters? I'm one that loves roller coasters. I'm kind of that thrill seeker type of person. But you know, whether you're talking about just a generic one like the Mamba that goes up really high and comes screaming down, and you have the hills. You think about the Patriot at Worlds of Fun. It's got upside down. It's got corkscrews. It's got all kinds of twists in there. But when you think about a roller coaster, you know, you always start down kind of at the base or at the ground. Okay, and then all of a sudden you've got the engine or the motor. It's going to basically, a chain's going to pull you up to this highest hill. So work has to be done. A force is being applied to that car, getting it up to its highest hill. And then once it gets to its highest hill, all of a sudden gravity takes over and it goes down. It goes through the corkscrews. It goes up and down. So force is being applied over a certain distance and getting that roller coaster to kind of do the rest because of gravity. So all of those changes in motion, the speeding up, the slowing down, the changes in direction, all of that comes from energy. And I know I use the word work, but you're going to see your definition of energy coming up here. Energy is that ability to do work. Okay, so are they the same? No, but anytime you have energy, okay, what we're saying is it can do work, it can do damage, two things. Okay, so I'm going to be going through some examples talking about energy, and we'll talk about the work and stuff like that. Work can be thought of as a transfer of energy. For example, if I take a shot put and I lift it up, and we'll say we place a styrofoam cup underneath. Okay, and the minute I let go, okay, I did work on that shot put and lifting it up. But then when I let go, that transfer of energy is going to come down and smash that cup. Okay, so that's kind of how that relationship exists between work and energy. So we're transferring energy. I'm going to do work, and I'm going to transfer energy to something else. Because energy is related to work, energy is also going to be measured in joules. Work, we just got done talking about it, it's measured in joules. So therefore, energy itself is also going to be measured in joules. There's going to be 6 types of energy that we're going to end up talking about. Now, in this video, what you're going to do is we're just going to actually talk about the first type because it's going to get broken down. So we're going to spend a lot of time on it. And then in the next one, what we'll do is we'll talk about the final 5 types of energy. The first one is going to be mechanical energy. It's energy that is going to be associated with either the motion of an object or the position of an object. And I'm hoping you're seeing here, well, motion is going to be one thing, position is going to be another. So these are going to be your 2 different types of energy. And what we'll do is we'll describe those. Those 2 types of mechanical energy, first one is going to end up being kinetic energy. Second one is going to end up being potential energy. Kinetic energy, that's the one that's in motion. Whether we're talking about a high-speed bullet or we're talking about a slow-moving turtle. Okay. Anytime something is in motion, it has a certain amount of kinetic energy. Kinetic energy is going to depend on 2 things. Number 1, the object's mass, and number 2, the object's velocity. Now you might be thinking, well, wait a second, isn't that momentum, mass, and velocity going to be slightly a different equation? But you are correct, momentum did deal with mass and velocity. If we have a bowling ball and a golf ball moving at the same speed. So notice we're keeping velocity the same. The bowling ball will have the greater kinetic energy because obviously the bowling ball weighs a lot more. Think of it as that bowling ball being able to do the greatest amount of work. Remember when I talked about dropping a shot put on a styrofoam cup? Well, if I take a golf ball and I drop it, it's going to hit it. I don't know, maybe it might crack it. But if I drop a bowling ball on a styrofoam cup, it's able to do more work of applying its force and getting it to crush compared to the golf ball. When we go ahead and we calculate kinetic energy is going to be equal to 1/2 multiplied by the mass multiplied by the velocity squared. Now, here's the thing. When we go ahead and we look at this, okay, there's going to be a parenthesis that really goes around this right here. Okay, we're not squaring all of this. What we're going to do is we're actually going to take the velocity squared first and then multiply it by the mass and then divide it by 2. Okay, that's where that 1/2 comes in. So kinetic energy is 1/2 mv squared. And remember, we have to square that velocity first. Mass has to be in kilograms. Velocity has to be in meters per second. And kinetic energy, as we said, energy is the ability to do work, so therefore it's going to be measured in joules also. So I want you to think of this. What happens to the kinetic energy when the mass is doubled? So if this gets 2 times bigger, this also is going to end up getting 2 times bigger. Okay, so kinetic energy gets doubled. But let's look at this one. What happens to kinetic energy when the velocity is doubled? So our velocity is going to get 2 times bigger. But notice this squared out here. So what is 2 squared? Okay, I'm hoping you said 4. And you're going to find out that that kinetic energy is going to get 4 times greater. Kinetic energy and mass, they're directly related. So if one goes up 2, the other one goes up 2. If one goes down 3, the other one's going to go down 3. But kinetic energy and velocity, they're directly related, but it's with that velocity squared. So as I said, if this got 2 times bigger, this got 4 times bigger. If this goes down 4 times, this goes down 16 times. So if we look at an example problem, it says how much kinetic energy does an 8 kilogram object have if it is moving at 5 meters per second? So again, here's our equation. Kinetic energy equals 1/2 mv squared. We're going to go ahead and plug this in. Okay, so I'm going to look at this. Here, we got to do this first. So 5 squared. 5 squared is 25. Okay, I'm going to go ahead and look at this. Well, half of 8. Half of 8 is 4. 4 times 25? 100 joules. Okay, so 100 joules worth of energy is possessed by an 8 kilogram object moving at 5 meters per second. The second type, that's potential energy. That's the one that's going to be due to an object's position. Okay, so it's the energy that is stored or held in readiness. And you're going to find out that there's actually 2 types of potential energy. The first one is going to be elastic potential energy. Potential energy because of the stretch. So if you look at my rubber band here, okay, if I pull it back a little bit, okay, it wants to get back to that normal position. But you know that if I pull it back a lot more, it can have a lot more energy, or it can possess a lot more work, or be able to do more work because of the greater amount of stretch that it has. The second one, this one has an equation with it. Okay, it's gravitational potential energy. It's the energy that an object has because of an object's position above the ground. The greater the distance above the ground, the more energy it has. I mean, if I take a golf ball and I just have it a little bit above my hand and I drop it, I mean, I'm going to feel it. But if I take it up here and I drop it from a lot higher and it comes down, it's probably going to hurt a little bit because it has more potential energy the higher it is above the ground. Gravitational potential energy can be calculated in 2 ways. The first one, gravitational potential energy, is going to be equal to the weight of the object multiplied by the height of the object. What you're going to do is you're going to find out that weight is in newtons, height is in meters, and gravitational potential energy will end up being in joules. So if you want this circle equation, you're going to have the gravitational potential energy here, you're going to have the weight down here, and you're going to have the height there. Weight measured in newtons, height measured in meters, gravitational potential energy is going to be measured in joules. The second way to calculate it is gravitational potential energy is equal to the mass multiplied by the gravity multiplied by the height. Well, the reason why we can put this one in here is because of this right here. Last chapter, or the chapter that we just came off of, chapter 10, when we talked about force and we talked about Newton's second law, you calculated out, or you learned, that the weight of an object was going to be equal to the mass of that object multiplied by gravity. So if I give you other units, if I do not give you the newtons, you will have to calculate out the weight of that object by just taking the mass multiplied by the gravity. Now, if that occurs, mass has to be in kilograms. Gravity, now that's not a negative, that's just my hyphen there. Okay, gravity, negative 9.81 meters per second squared. Height, still in meters. Gravitational potential energy in joules. So notice the difference here. They both have H. It's just, do I give you the newtons where it's calculated out, or do I give you the kilograms where you have to calculate the mass multiplied by the gravity and then multiplied by the height? So let's look at this example problem, potential energy. It says how much potential energy does a 100-kilogram object have 20 meters above the ground? Now, don't just look at this and say, oh, I must be using the first one because I only have two things here. And the first one was W times H. But notice, there are no newtons here. Okay? And if you don't have newtons, that means that you have to go to the second one. So we're going to use this one. Potential energy is going to be equal to the mass of the object. That's the 100 kilograms. That's going to go right there. Gravity, that's going to be that negative 9.81. The height is going to end up being 20 meters. Now, here's one thing I want you to look at. Look at what I did. Negative 20. Because if it's up here, where's it going to go when gravity takes effect? Down. So down on that y-axis ends up being negative. Okay, we can't have negative energy. So we're going to take 100. We're going to multiply it by gravity, negative 9.81. We're going to multiply it by the distance that object's going to fall, 20 meters. And when we multiply everything out, you're going to find out that that object is going to have 19,620 joules worth of energy. Now, what I'm going to have you do is I'm going to have you do a worksheet that's going to be over work, potential energy, and kinetic energy.